One of the most incredibly diverse clades of organisms is the animals. They're some of the most complex organisms on the planet. They exist at macro and microscopic scales. They're extremely influential drivers of ecological processes, and they've been around for hundreds of millions of years, enabling animal life to diversify into the breathtaking range and diversity of species that we see today. The evolutionary history of animals is particularly interesting, and like most histories, there is a beginning somewhere, as an abstract point or phase during an evolutionary transition wherein the earliest animal ancestors diverged from their soon-to-be cousin lineage of fungus. Studies of animal genetics and phylogenies suggest that this earliest common animal ancestor lived sometime in the Neoproterozoic era, which is a broad, approximately 550 million year-long chunk of time that began about a billion years ago. Within this time period, within the Neoproterozoic era, some pretty important things happened. About 800 million years ago, oxygen began accumulating in the atmosphere and dissolving into the oceans. This process lasted for almost 250 million years, and it's known as the Great Oxygenation Event. It's believed to have been responsible for creating the conditions that enabled animal life to thrive. Also in this time period, there was a brief 80 to 90 million year period that began about 720 million years ago, when the Earth underwent the cryogenian glaciations and was often covered mostly or nearly completely in ice. When the Neoproterozoic came to an end with the Cambrian explosion around 451 million years ago, it marked both the end of the Precambrian and the beginning of the Paleozoic era, the first era of the ongoing Phanerozoic eon. In our ongoing exploration of our planet, discoveries of fossils, and subsequent analysis of Earth's evolutionary history, we've built a pretty robust timeline of the speciation of the animal clade. Of course, there are many areas where the data is lacking, either because the genome is difficult to crack, or the animal is rare or difficult to study, or in many cases there just isn't a sufficient fossil record, and huge portions of their evolutionary history lie in mystery. From what fossils we have gathered, some of the oldest, representing some of the earliest animals ever evolved, can be dated to approximately 665 million years ago, from the Trizona Formation in the south-central state of South Australia, which formed during the middle of the Neoproterozoic. The fossils depict primitive sponges, which lived on the seafloor and sifted food out from the flowing water. Now recently, a new study has been published in the journal Nature that may overturn these as the oldest animal fossils. Now, these results have to be further analyzed, and a lot more research is needed to verify some of the claims made in the paper. But for now, this remains a very exciting bit of news. The study has a single author, Dr. Elizabeth Turner, a professor at Laurentian University. From 1992 to 2018, Dr. Turner collected fossil samples from a mountainous region in a remote, difficult-to-access region of northwestern Canada near the Mackenzie River. This mountainous region was once an ocean floor containing coral reefs, and the fossils of these reefs are embedded in the Stone Knife Formation. The reef fossils are half a kilometer thick and kilometers in diameter. Dr. Turner took her samples from these massive fossil reefs. In her paper, she discusses how some fossilized sponges have been found to have vermiform microstructures, which are, quote, too consistent and complex to be abiogenic. For example, compacted peloids do not resemble the branching style of other possible organism types, microbial or fungal, and are identical to the sponge and meshworks of keratose sponges, unquote. In the results section, Dr. Turner provides analytic comments on the morphology of the samples and their distribution in the substrate, noting that the, quote, vermiform microstructure preservation is good to barely discernible, which you can see in some of the images in Figure 2. Ultimately, she concludes that the, quote, shape, size, branching style, and polygonal meshworks of the little dowel vermiform tubules closely resemble both sponge and fiber networks of modern keratose sponges and vermiform microstructure, either demonstrated or interpreted to be sponge-derived in diverse Phanerozoic microbial, reefal, and non-reefal carbonate rocks, unquote. The discussion section of the paper is really interesting, but it's a bit long, so I'm just going to give you some of the highlights. The evidence indicates, by nature of the vermiform microstructures, that this is fossilized sponge tissue, as there is, quote, no convincing alternative to the sponge interpretation, unquote. There was also discussion of the lack of photosynthetic calcimicrobes in this habitat when it was active, and the lack of sponge fossils in areas where there were filamentous calcimicrobial reef activity. This would suggest that the sponges were perhaps unable to compete with the photosynthesizers at these reef habitats. I didn't know what a calcimicrobe was when I first read this, so I looked it up. Apparently, it's a varied collection of microbial clades that synthesized or somehow precipitated calcium salts, and in combination with similar efforts made by primitive shell-secreting animals like ancestral bivalves or some such creature, their cumulative activity deposited massive shelves of calcium minerals that were, effectively, the planet's first true reef ecologies. Dr. Turner suggests that, quote, prior to the Neoproterozoic oxygenation event, marine dissolved oxygen was probably low, except perhaps in the vicinity of photosynthesizing microbial communities. The metabolic requirements of metazoans may have limited early animals to localized, comparatively well oxygenated, for the time, environments like oxygen oases. Given the approximately 890 million year old depositional age, the vermiform microstructured little dowel organism may have been tolerant of low oxygen, that is, relative to modern levels, which is a characteristic of some modern and fossil sponges, unquote. Okay, so did you catch that little detail there? The age of the rock samples? The stone knife formation, and thus these sponge fossils, are 890 million years old. If these findings can be verified, this is big news. This would be evidence, quote, that 1. The evolutionary emergence of metazoans was decoupled from the Neoproterozoic oxygenation event, and 2. Early animal life was not catastrophically affected by the Neoproterozoic glacial episodes. If the little dowel objects are truly sponge body fossils, they are older than the next youngest undisputed sponge body fossils in the Cambrian by approximately 350 million years, unquote. In addition, this evidence suggests that the Opisthokonte clade, which includes both common ancestor of the animals and the fungus, existed well before the Neoproterozoic era. Studies using molecular clocks have estimated the origins of the sponges were around this time period, which further reinforces the finding. Dr. Turner concludes that this is evidence of, quote, perhaps exactly what should be expected of the earliest metazoan body fossils: preservation through post-mortem calcification of sponge-grade soft tissue in the decaying bodies of small, shapeless, sessile, epibenthic, and cryptic animals most closely affiliated with keratose sponges, unquote. Man, this is a great paper. The finding is incredible. It's literally 350 million years older than the next oldest thing, so the potential implications for evolutionary history are pretty big. The paper itself is also extremely engaging, well-written, and enjoyable to read. Evolutionary history is cool as hell, and discoveries like this are badass and super fascinating.